Now, a couple of remarks on the topic of today. I mentioned already that we do make DD fusion reactions in warm fusion, but mostly we see a lot of neutrons to go with it, or a lot of protons, and there haven't been any surprises on that score. The thing has worked exactly as predicted by nuclear theoretical physics. In theory, it is possible to make directly a helium also plus a gamma. It would be hard to fail to notice that gamma, however, because it's a very energetic gamma. It's also conceivable that the branching of reactions would be different in cold fusion from warm fusion, but it's a little surprising because the only experience previously we have with cold fusion is mu meson catalyzed fusion, and for that the behavior is exactly as for warm fusion, and there is no evidence that the helium branch goes. So nuclear physicists at the moment are puzzled by the aspect of the cold fusion experiments, which is that the neutrons seem to be down by some very large factor, variously reported, I think, as 1 billion or more, relative to what one would expect from the energy release. And that puzzles them because that would call for some unusual prominence of straight helium production, perhaps with the lattice carrying away the excess momentum rather than a gamma ray. And that's puzzling, first of all. And secondly, what's more puzzling is that the usual reactions should be suppressed if the deuterons are so cozy that they're doing the helium. And somewhat similar remarks apply to D-lithium-6. There are reactions that would quietly make more nuclei that wouldn't be very conspicuous, but the puzzle is why doesn't one see the conspicuous reactions which are actually more probable. So I think that's just something for nuclear theorists to chew on. Next slide. Little something about reactions of different hydrogen nuclei in cold fusion. Let's look first of all at the normal molecule. The normal deuterium molecule has a very low rate of fusing spontaneously by tunneling, you know, like sort of once in the life of the galaxy or something of that sort. Not very useful. On the other hand, we can ask, what about deuterium-tritium? And there we find deuterium-tritium actually goes even more slowly by 6 orders of magnitude than ordinary deuterium because it's heavier, and so it doesn't tunnel as well. By the same token, hydrogen deuterium goes more easily because it's lighter, it tunnels more easily, and so that would actually go 10 orders of magnitude faster. Now, if only you could see the top line there, it would tell you if we conceptually shrink the molecule by imagining that the electron mass is heavier, so as to bring the nuclei closer together so they'll fuse more easily, have an easier time of tunneling, how do the rates go then? And it tells you that if the electrons were about 6 times heavier than they are, one could reproduce the Brigham-Young kind of results, which are about 10 to the minus 23. And if you get a little heavier yet, you can get the Utah U results. And then somewhere off to the left is what you would get with mu meson fusion, the mu meson being some 200 times heavier than the electron. That goes very fast. And now again, the DT, as we are now going to more promising conditions, is getting more prominent relative to the DD, but it still hasn't caught up with the DD. And the hydrogen D has sunk, but still it should be clearly visible if the DD is visible. Next slide. And so that leads me to one remark which I think is sufficiently obvious so that about 100 people in this audience have thought of it too, but let me make it nonetheless. Namely, instead of everybody sticking palladium into heavy water, some fraction of the population should be sticking palladium into half and half. Light water and heavy water. 5.5 MeV gamma ray of the PD reaction alongside this 2.45 MeV neutron of the DD reaction. And that is the merit that the gamma ray is at least as likely and will become relatively more likely if the reaction is going poorly. The more pessimistic you are, the more you should be looking for the gamma ray. Secondly, the detection equipment you need on the whole may be cheaper, as it would be in our laboratory. Thirdly, if you're trying to make up a theory of how all this works, then knowing the ratio of PD to DD would be most valuable. Like if they're comparable, then tunneling is going to have some importance. So that's not to say that there aren't chemical differences between hydrogen and deuterium diffusion into metals also, but to get a rough measure of this ratio would be of immense value. I think really the most fundamental thing that needs to be done at the moment isn't meditations by nuclear theorists on whether this is crazy or plausible or whatever, but a little work by the American Chemical Society where you repeat the experiment producing excess heat in heavy water and then reproduce that exactly using ordinary light water and compare the excess heat. I think that's really the key to it all, and we're waiting anxiously to see it. Could I have the last slide? Now, finally, I should say something about why we're interested in fusion at all. And this graph, which is made at Livermore, I think is quite useful. It takes a fairly optimistic view of world energy consumption. World energy consumption is this line drawn here. It assumes that the world population will level off at a mere 10 billion and that they will be content to live at 2/3 the present U.S. Standard of living, at least energy consumption. And so that means that there's going to be quite a rise in annual energy consumption. The second curve shows you how we're doing on energy that's easily available by taking fossil fuels out of the ground or hydroelectric or burning up the readily burnable uranium and such stuff. And you see we're doing awfully well in consuming that, then it's about to keel over and go the other way. So there's a gap that will develop. That gap can be bridged to some extent by things like solar power, which is very effective for peak heat loads in nice weather. But in rainy weather and at night, you would like some kind of base load power source. For that, fission is a good choice, except it has made itself unpopular. And so in many people's minds, fusion would be an even better choice because it would provide a long-term solution which both promises to be economical and to have no highly adverse environmental impacts. Now, how soon do we need it? The divergence between power needed and power available will take place, according to this graph, around 2040. Knowing how quickly the utilities industry responds to new ideas, that means you better know exactly what you want to do 30 years earlier, namely around 2010. And so, really, there isn't all that much time to be lost in identifying a really promising source and the most promising form of that energy source for meeting this long-range problem. One thing that always strikes me about this graph is it's sort of a mere 300 years to blow the entire bank deposit in the fossil energy bank, which was laid down over 400 million years so that humanity could advance to a high level of civilization. And we and our immediate descendants have the extraordinary privilege of blowing this entire bank account in 1/1,000,000th of the time that it took to accumulate. So I kind of visualize our descendants in the year, say, 2350, looking back and thinking about us. and wondering what we had in mind, and whether there's anything redeeming to be said about us. And I think one of the few redeeming things that could be said was that we devoted some very small fraction of this bank to developing a new energy source which could keep civilization going after we've blown all this stuff. And if by chance we could succeed in developing fusion as that energy source, then people may think we weren't altogether bad. And so I very much hope it works out that way. Thank you.